Okay, so for experiment number 8, you will be testing and determining the concentration of water hardness ions present in Morgantown's municipal tap water. And how you will do this will be via titration. So this experiment should be very similar to that of what you did in experiment number 6, where you used a titration method in order to determine the unknown concentration of citric acid in drink mix. With this experiment, however, you'll actually be doing two different types of titration. You will be using soap suds in order to determine the concentration of water hardness ions present in tap water, and also EDTA in order to determine the concentration of hardness ions present in tap water. So there's two different methods, two different types of titrations that you're going to complete while doing experiment number 8. Now, in terms of titration, you already know that you can use it in order to determine an unknown concentration. So for this experiment, you're going to determine the unknown concentration of calcium ions in municipal tap water. So if we look at the pre-lab questions, question number 1 says that we have a 25 ml sample of municipal tap water, and it requires 12.66 mils of soap solution before the appearance of permanent suds, and this is very similar to what you will be doing in lab. Now, if the 1 mil of soap solution titrates 0.78 milligrams of calcium carbonate, what is the milligrams of calcium carbonate in the 25 ml sample of tap water? What's the milligrams of calcium carbonate per mil of tap water? And what is the parts per million calcium carbonate in the tap water? So there's 3 different parts to this question. So in order to answer the first part, the milligrams of calcium carbonate in 25 mils of municipal tap water, we have to take a look at the problem and see what we have here. So what we see is that we have 12.66 mils of soap solution. So if we compare this to what we did in experiment 6, this would basically be the base that we are using, the amount of base that we use when we reach the equivalent point. So this is actually the number that we want to start with. So we have 12.66 mils of soap solution. Now, we want to determine the milligrams of calcium carbonate in this soap solution, or in this 25 ml sample of tap water. Now, we need a conversion factor, because right now we're talking about soap solution, but we need to be talking about milligrams of calcium carbonate. So, if we look and see what we have in our problem, we see that for every 1 ml of soap solution, it titrates 0.78 milligrams of calcium carbonate. We can use this as our conversion factor so that we cancel out mils of soap solution, leaving us with milligrams of calcium carbonate, which will essentially answer part A of this question. So if we set it up correctly, we know that we want to cancel out soap solution, leaving us with milligrams of calcium carbonate. So we put calcium carbonate on top, and we have 1.00 milliliters of soap solution on the bottom. So if we cancel out our units, mils of soap solution cancel, leaving us with milligrams of calcium carbonate in the 25 mils of municipal tap water. So this answers part A of the question. So when we do our calculation, we get an answer of 9.8748 milligrams of calcium carbonate. Now, we always have to pay attention to significant figures, and we see that for this number it has 4 significant figures. This has 2 sig figs, while this one has 3 sig figs. And since we are multiplying and dividing, we know we go by the fewest number of significant figures. So our answer for part A would be 9.9 milligrams of calcium carbonate. Now, to answer part B, we see we want the milligrams of calcium carbonate per mil of tap water. So what we have right now for A is simply the milligrams of calcium carbonate. Now we want to know the milligrams of calcium carbonate per milliliter. So essentially what we have to do is divide by 25 milliliters. So Since we are using this number, we want to make sure that we use the unrounded number. So we have 9.8748 milligrams of calcium carbonate. And since we want it per milliliter, that means that we have to divide by the sample size, so 25 milliliters. So we have 25 milliliters here, and when we do this calculation, we get an answer of 0.394992 milligrams per milliliter of calcium carbonate. Now, and you see that none of the units cancel out. We have to pay attention to significant figures. Here, with this number, even though we're using 5 digits, we know that only 2 of them are significant from the previous problem. Here we have 3 sig figs, so we know when we report our final answer for part B, we can only have 2 significant figures. So we've done part A, where we have determined the milligrams of calcium carbonate. We've done part B, where we've determined the milligrams per milliliter of calcium carbonate. The last part that we want to determine is part C, which looks at the parts per million of calcium carbonate. And basically what parts per million is it is a specific unit. And there are several to choose from, but in this particular problem, the easiest one for us to indicate parts per million is going to be milligrams per liter of calcium carbonate. Now, if we look at part B, we already have milligrams per milliliter. So if we convert milliliters to liters, then we have parts per million of calcium carbonate in the tap water. So if we take our original number from part B, and it is milligrams of calcium carbonate per milliliter, and if we convert that to liters, then we will have parts per million. So we know that for every 1,000 milliliters, there is 1 liter. So if we cancel our units, milliliters cancels, leaving us with milligrams per liter, which is a unit of parts per million. So when we do our calculation, we get a value of 394.992 ppm calcium carbonate. But again, we want to pay attention to our significant figures, and we know that this number here has 2 significant figures, even though we have to write all of the digits. This here we know is a conversion factor, and we consider it to be exact, so we do not include it when determining significant figures. So what that tells us is that our final answer needs to have 2 significant figures. So this would then become 390, but we know that when we have a number ending in 0 without a decimal place, we have to write it in standard scientific notation. So we would have 3.9 times 10 to the 2 parts per million of calcium carbonate.